So, you make your mom some tea, and then you ask her how many spoons of sugars she would like, right? And then you write that down. Is that data? Well, it's data if your mom represents maybe something like elderly ladies, and you're trying to make a tea shop for elderly ladies, right? If you ask your mom and she say, "Oh, two teaspoons, please," and then you record it, that's already information about your mom. However, when would this make a data? Well, what if your mom changes her mind? Sometimes she likes 1 teaspoon, sometimes she likes 2, right? And the population is not some elderly ladies, but the population is your mom in the future, right? You're not serving just your mom right now. You're gathering information so you can better please your mom tomorrow morning, right? And maybe, after you gather enough data, you realize that, oh, okay, you know what? She likes 1 teaspoon if she's having toast. But she likes 2 if she's having eggs or something. I don't know. Okay? See what I mean? So what makes it a data? What makes it just immediately information? A good maybe rule of thumb would be, can you act on it? Can you make decision? Can you make some kind of, do you get insight right away, or you need this to basically put in some kind of model? Okay? So data is more of a raw material. Right. So what makes a data point? Okay. Now here's an interesting exercise that I literally draw upon. Okay. You have a screen, computer screen, right? Let's say we have 1,024 pixel wide and 512 pixel tall RGB screen, luminosity of each color between 0 and 63. I'm just making it seems like a digital thing because everything is power of 2. How do you define a data point? Right? Now, this is already in a digital machine, right? But to make it data, you have to digitize in data format. How do you make it? How do you record this? How do you record? So let's try method 1. So 100 times this, times this. So it has that many points. Okay? So in this case, you don't have to worry about this, but I'm going to shift enter. And it say, well, it has, let me see. Let me make sure I don't give you the wrong. For this scheme to work, its point has to have 3 more. Okay? So you have 3 for hues. You have 2 to the, where are my glasses? Right? So you have luminosity, you have pixel, location, horizontal, vertical, and line. So there. Method 2, the data set. So we're talking about data versus data set, right? So you have, now you can have many data sets, but let's say just one data set. So a bunch of one. So there it is. Method 2, each data has this many points. But the point themselves, each point has 3-dimension number. By the way, this is more sensible because each pixel has 3 colors, right? Red, green, and blue. So there, that's another dimension. Now, the way you actually work is you actually have what's called a tensor. Basically, if remember in high school algebra, you have matrix, right? Matrix is just a rectangular array of numbers right? What's important is that the dimension define the class of matrix. So a 3 by 4 matrix is not a friend of a 7 by 8 matrix. Okay, in fact, they can't interact. Okay, but a 3 by 4 matrix may do something with another 3 by 4 matrix. It may also do something with a 3-dimensional vector. It may do something with a 4-dimensional vector. It may do something with a 3 by 7 matrix. It may do something with a 4 by 8 matrix. Okay, so in a way, you think of like this thing like a UBS, UBC plug thing, right? You have to have the kind of dimension that match, otherwise there's no interconnection. Well, it's that sort of thing. Well, right now, a matrix is just rectangular array, but if the array looks like a flat screen and each pixel has 3 colors, you can think of a 3 axis. There's horizontal, there's vertical, and there is the color selector, right? Red, green, or blue. Now, by convention, red comes first. So if you give a number that scale from 0 to 100 or 0 to 1, and I give you a color. What color am I thinking of? I'm thinking of a 100. You should say, that's a red, right? Because max is 1, and red is the first one, so that's 1. Blue, 0. Green, 0. So that's pure red, bright red. What about 0.500? That's a darker red, right? What's 000? That's a black. What's 101? Red, no green, blue, purple, right? So that's a tensor. This is just to get your mind going, okay? Data versus number, okay? This is nice. This is about Sumerian culture. You can read that on your own. Now, this is something important. You don't get this right, you shouldn't graduate. Why do I say that? It's one of the easiest things in the world, and yet professional data scientists make error on this. It's just they're not mindful, okay? If I told you earlier, number does 2 things, measure and count, right? Right? If I want to generalize, I want to say, well, I don't want to use the word count anymore. Okay? So I create an abstract ruler that helps count. So if I count number of students, 1, 2, 3, 4, it's like I'm counting little knots on the ruler. Okay? Conceptually, right? In which case, everything is a measurement. Every number is a measurement. Okay, except that this counting thing is about measurement of multiplicity. On a multiplicity ruler, this has 5. That means 5, right? So everything is a measurement to scale. Now, let me ask you this. The stick that has centimeters in height, that's very fine-tuned, right? Because you can go to 1/10 of a centimeter. How about multiplicity scale? You can't. There's only 1, 2, 3, and 4, right? So not all sticks are created equal. Okay? This is what I want you to be mindful of. Numbers is rate off of sticks. Not all sticks have the same level of information. If you take something that has level of information of 0, 1, 2, 3, and you try to count 3.5, you won't be able to do it. Okay? The point is, sometimes professional data scientists make error because they mix their scale. So I want you to be mindful of the 4 canonical scale. 1, nominal scale. Nominal scale comes from the word name. So a scale is a name. It's not an accumulation. Your student ID is a nominal scale. Okay? Technically, if you have a higher student ID number, are you a better student? No. Right? Maybe the only thing you can say is that who came first. But beyond that, nothing. Okay? A student that has an ID of 1, 2, 3, 4 and 4, 3, 2, 1, I can't tell them apart. Well, I can tell them apart. I can't say what more than that. So what's the mathematical operation you can do with this kind of number? Check sign, equal or not equal. That's it. That's the only operation. Okay? That's the only logical question you can ask. Is 1, 2, 3, 4 the same as 4, 3, 2, 1? No, different student. So the only valid operation is inequality. This is what I mean by this is the simplest thing that professional data scientists do, because sometimes they create a model that gives a ranking A greater than B, when in fact A and B are both nominal, right? That becomes erroneous in the inference, okay? Sometimes it's not so bad, sometimes so that's it, inequality, nominal scale. Okay, now let me do this. Let me delete our output. Okay, so right now, by the way, we're going to do introduction to Mathematica, and you're going to see that later. But just like Jupyter Notebook, there's cell, right? So this cell, if you look, let me make it bigger. So these are basically instruction. My question is 3 equal, okay? That's a question. 3.0. Now, in this case, because 3.0, even though 3.0 can be something like precise, like centimeter, and 3 is number of children, so you can't have decimal. So technically, counting number and decimal number don't belong to the same universe, right? But in this case, it's for practical purpose, yeah, it is. 3 is the same as 3.0. So if I shift enter, I get through. Okay, I get through. Okay, and that's all you can do. Is 120 equal to 5 factorial? Anybody? What's 5 factorial? Okay, so that's true. Well, in fact, just to make the textbook look nice, everything here has true. Okay, now this is where something right away tells you that we're dealing with something way beyond Python. You have something like factor, right? This is not a library. It's a built-in function. I don't have to import matpy or anything, okay? And it's not numerical, it's symbolic. So it factor a cubed plus 3a, but from high school, you know this. Is this true? Yes, of course it's true. Okay? This is also true. This is symbolic. Pi, I, and E. Once again, these are things that, in Mathematica, you can actually put in infinity, and it knows what infinity means. You can't do that with numerical method or C or Python or Java. It doesn't know what infinity is. But this one does. So, is Alice Bob? Alice is not Bob. So everything is true. Okay? Now, let's move on to ordinal scale. Ordinal scale means you have order. So you can say A is greater than B. Okay? In some sense. Okay? Now, let me give you this. Example would be, I can sort my character. This is my name. Why? Because there's an inherent order implied by the alphabet. A comes before B. So it's A, C, so this is sort, right? But how far away is A from B? Can you do that? No. You only know that A is greater than B, or less, in this case, less than B. A come first. Same thing with beauty pageant, right? And there's a Miss Universe, there's a runner-up, the second runner-up, third runner-up. Can you say how much more beautiful is the Miss Universe from the first runner-up? Can you take a distance? You can't, right? You can only do greater than, equal to. That's a mathematical operation you're limited to. Okay? Now, next, interval. Now you can subtract. Right? If a gymnast perform a routine and gets a 9.7 score, and the other one gets a 9.2, what's the difference? 0.5. Right? There is a sense of how far. So you can have a gold medalist get 9.7, a silver medalist get 9.6, and a bronze medalist get 8. And this will tell a story, right? Separate. The story will be, oh my God, the gold and the silver are so close together, right? As opposed to gold medalist is 9.7, silver medalist is 8.1, and bronze medalist is 8.0. In which case it's like, no contest, guys, right? So there's a difference. That's a difference. You can take subtraction, and that's why it's called interval scale. Now, how about, can you say that a gymnast, okay, who gets a 9 and the other one gets an 8, it's 9 to 8. It's 9 divided by 8 times better. Can you do that? You can't really, because this scale is kind of arbitrary, right? In fact, for a gymnast, a 0 on a competition is better than what your knees can do, right? The best routine that your knees taking a gymnastic lesson is not even a 0 on a Olympic scale, right? So that's kind of arbitrariness, right? You can't say how many times is one better than the other. So you can't have any kind of ratio. Okay? Another example. This room is 25 degrees centigrade. The other room is let's say 30. Can you say that room is what, 130 divided by 25 times hotter? Can you say that? No, because when you say it in Fahrenheit, you get another ratio, right? Because the 0 is completely arbitrary. Okay? Right? So that's why all you can do is subtract, but you can't divide. If you can divide, then it becomes a ratio scale. What it means is that not only can you measure distance, there's an absolute 0 to it. This is very important. In fact, I don't know this for a fact, but remember I told you that professional data scientists mix and match this category of numbers, and they make more conclusions that they should make. Okay? So they would end up, and obviously this is silly answer, the silly solution, say something like, this company or this design is 20% better than that design. Okay? So if you can do this, that means it is a ratio scale, right? But it turns out that the number they work with doesn't have that 0. There's no absolute 0. So making a statement like, this design is 20% better than that design, that means nothing. Now, that sounds obvious to you, right? But believe you me, this is very important, because data scientists, make mistakes like this all the time. This is one of it. It's about mindfulness, guys. It's not about technical brilliance okay. So be careful. So the first thing is, so I give example of this, right? You can sort. By the way, in Mathematica, I can have a different problem. It's a little bit like intelligent, so it does go and look up. So here, it literally goes out on the internet or whatever, that knowledge base. So it actually looks up human body temperature. Okay, so this is kind of like except the difference between this and Googling is just what's out there. What this is actually curated data. So yeah, human temperature versus mice temperature is about, the difference is about -2 centigrade. Okay, ratio scale, you can do sun mass, earth mass. Oh, 333,000 times bigger. Okay? And you can expand. So this is more than obvious Jupiter. You can expand this. This is called Wolfram Alpha. What it means is that it's not just computation, but it has a curated knowledge base. So I can ask something like, well, we can find out about people. Alan Turing. Alan Turing. See if I get something. Mathematician, born, place of death, image, timeline. Okay? And this is even better than, in a way. A lot of times this is more precise and to the point than Wikipedia page. But it does, yeah, it recognizes Wikipedia page. You can bet that this is the time the movie Imitation Game came out because people search him around that time. Okay. Anyway, so you have to know between different scale of number. That's very valid, and I will be sure to ask you that during the exam. Because it's something I want you to be mindful. You should be punished for not getting it right. Okay? Dimensionality of numbers. Right? So there's kind of like a hierarchy, a scalar. Well, what does the word remind you of? Scale, right? A scale is a number you write on a stick. Okay? It's just a number you write on a stick. And you can only write one number next to each mark. So scalar is just one number. Okay? Scalar is just one number. Okay? Everything that I mentioned before, scalar can belong to all four scales. So scalar and scale here means different things. Scale means scale of measurement, the degree to which you can imply comparison. You can only do inequality. You can do greater than. You can subtract. You can make ratio. Okay? So nominal, ordinal, interval, ratio, scale. Okay? Those apply to the number. Now, if it's just one number, then it's called scalar. Okay? Same word, right? So something rate of some scale. Okay? 1 of 4. Vector means you have a pairing. So that's a 2-dimensional vector. Triplet, 3-dimensional vector. Any number, right? So you can have 300-dimensional vector, right? Why is 300 a magic number, anybody? Roughly speaking, it's what I use to represent words in English. Words get translated into numbers as well. And that is sort of like, well, that's almost takes you all the way to the end of the class. You say, wait a minute, if words can be turned into vector, and vector can do this subtraction and all kind of stuff, maybe you can do subtraction with words. And that's precisely the power of large language model. You can do addition and subtraction with words. Okay? Now, to give the game away, the story away, you've probably seen this already, example in other class. King is a word. Queen is a word, right? Male is a word. Female is a word. So if you take the word king and subtract the word male, add the word female, you get queen. Right? It's not exactly like that, but you know, this is the example we use to say this is how large language model can do inference, because it does have this algebra, addition, subtraction, operation, multiplication even. Okay? How about a boy, older boy, adult, older adult, senile or senior or whatever, right? So you multiply adult with older or something like that. Okay, so this kind of word algebra, just something that's going to be very relevant for like language model. But anyway, right now let's talk about this. Vector is an ordered list. Why is it an ordered list? Because 2 and 3 is not the same thing as 3 and 2, right? And the first thing you can think about of vector is it's good for locating stuff. So if I have 0 mark here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 0 here to 10, you may be sitting at 7 and 2.5, right? That's not the same thing as 2.5 and 7. So it's ordered, okay? Now in this case, it's horizontal and vertical, or left, right, front, back, but they're both location. But I can say something like location and weight, or height, or grades, okay? So it's arbitrary. It can be anything. It's completely general, but you have to define it, okay? And once I say something like x1 and x2, x1 is the weight, x2 is the height, then you have to stick with that, right? So everybody comes in, you record the weight first, then the height, weight, height, weight, height, weight, height. You get the point. So this is kind of so an object is a scalar. It has dimension 0. An object is a vector. It has dimension 4. Now we talk about matrix. This is a matrix. A, B, C, D, E, F, G, H is a matrix because it's a rectangular array of number, except I haven't put in real number yet. So what's the dimension? By convention, you go with the number of rows, then the number of columns, right? So how many rows does it have? 2. How many columns does it have? 4. So it's 2. Now, it's written 2 and 4, but you don't say it that way. You say 2 by 4. 2 by 4. Okay? Now, how about this guy? 3 by 3. Now, normally a vector, it's a column vector. So it looks like this, but there's also a row vector. Now, this technically is something that matters in matrix algebra, right? You can only, you have a 4 by 4 matrix, right? You can post multiply with the 4 by 1 or vector, but if you want to pre-multiply, you have to take this thing and lie down, transpose it first, become a row vector, high school stuff. Now, tensor. Now, this is where it becomes more relevant to you guys. In my year, tensor is important because I was studying relativity. I did my undergraduate in physics and economics. So in the physics class, relativity, the Einstein tensor is a tensor, okay? But beyond that, nobody heard of tensor. But now that we have this screen, right? 124 by 512 by 3, that chunk of thing becomes a tensor. So now tensor is a very common word. So a tensor, a tiny screen, okay? A tiny screen. Let me show you one. Okay? Right. Now, why do I say this is a tiny screen? Because instead of having 512 rows of pixel, I only have 2 rows of pixel. Instead of having 1024 columns of pixel, I only have 3. So it's tiny. And the color value is red, green, blue. Okay? Red, green, blue. By the way, what does it look like? Now, you don't know how to do this yet, because I haven't taught you how to basically, I take this thing and then map it to a color. There it is. So this here is that here, 100. Okay? And this here, in fact, I can just do a random number. RGB color. Okay? Let's make it, so this obviously will be purple. right? But let's make it a little bit more red and not so dark. Whatever, okay? All kind of stuff. So that's. But definitely, here is a tensor because it has 2 by 3 by 3. 2 by 3 by 3. Now, because I wrap the color into an object, this is a 2 by 3 pixel, right? So 2 by 3 screen, 2 by 3 screen. Yes, it's a 2 by 3. So it's a rectangle pix of RGB. But the value itself is not 2 by 3. The value itself is 2 by 3 by 3. Okay? So this 3 here is the number of column. This here is because you only have 3 primary colors. Okay? So let's generalize the notion of data. So not data, not all data, and this is, we talk about large language model. We need to do this later, okay? But for most of this class, because we're learning about data analytics, how to deal with data, how to build model, how to do unsupervised learning, supervised learning, this basically deals with numerical data, okay? Again, I'll give a heads-up talk on working with text data, but that would be more in the realm of machine learning and AI, large language model. Okay. Now, this, however, this is important, and this is basically the last thing we need to cover today. Tabular versus graph data. Okay. This is basically how data comes to you. Well, how does data come to you? It comes in a zip file, it comes in a format this, format that. But no, forget it. Think of Excel, spreadsheet. Okay? A spreadsheet. Well, if you fill up all the numbers, all the cells in the spreadsheet, what would it be actually? It would almost be a tensor, wouldn't it? Because with row, column, but then you have multiple sheets, so you can think of it as depth, right? Anyway. But the point is, virtually 80–90% of your application maybe is dealing with what's called tabular data. Data that in a way can be formatted as a table. Tabular data comes from table. So you have to ask yourself, well, if it doesn't come in table, how does it come? Right? Well, in computer science, there are many data structures. You can do linked lists, you can do hash table, you can do JSON format, you can do hierarchical. There are many things. But in this class, the 2 things that you are going to have to learn, because it's going to be most relevant, are 2 forms: tabular data and graph data. Tabular data is so ubiquitous, it's virtually the baseline of all the database program and Oracle. Everything is based on a table. Okay? In fact, virtually all the database, professional database, is based on some kind of table. Okay? There's only 1 or 2 that I know of professionally used database whose basic underlying organizing principle isn't table, but a graph. Anybody knows? I haven't used it myself because there's a map between tabular data and graph data, and I just work off of tabular data and I create a graph. Neo4j, have you heard of that? They try to fundamentally represent data as graph, fundamentally. Okay, so it's not like right now. I do a lot of graph theoretic. In fact, my major research interest is graph, but the data, the graph data that I work basically gets saved as a table, and then I read it off and then make it a data, make it a graph. Okay, I'll show you why later. It's in chapter 7. Okay. Anyway, so the fundamental concept is row and columns. Data comes in row and columns. A tensor, well, a tensor is a bunch of tables stacked together. So instead of having an array of RGB color, you can have a flat array of red, a flat array of green, a flat array of blue, right? Conceptually, it's the same thing. So you can think of data saved on an Excel, maybe. An Excel has 512 row and 1024 columns, right? And the first sheet is for red, the second sheet is for green, the third sheet is for blue. There's your worksheet, there's your data, there's your screen, right? Yeah. Now obviously, that tensor, in fact, can you have higher dimension than that? Higher, well, it's not dimension in terms of number, but in terms of, add another depth, another axis. Can you add another axis to that? Sure. A movie, right? A movie has row, column, RGB, and timestamp, right? Right? So it is, let's say, okay, I'm just making it, the whole thing sound silly, but let's say this, you have a refresh rate of 60 frames per second. 60 frames per second, right? 60 frames per second. And how many seconds in a minute? 60, right? So a minute's worth of video can be recorded as 512 by 1024 by 3, red, green, blue, by 3600, right? Because you have 36 frames per second, and you have 60 seconds a minute, something like that, right? Now, there's no bigger word than tensor, so they call it tensor. Okay? So 2 by 2 by 3 is a tensor. 2 by 2 by 3 by 4 is a tensor. 2 by 2 by 2, everything from there is tensor. Okay. Now, graph data is different. Technically, you don't store numbers in rows and columns. Okay? Well, first of all, have you seen those network-looking things where you have nodes and lines between them? Right? Well, they store information or number in the nodes. You can also store numbers in the connection. Okay? Now, the simplest thing is just, instead of, I want to know who knows whom. Who knows whom? Okay? And I call you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 students. Right? So how many circles do I need to store your identity? 11. Right? Just forget about student ID. Just use 1, 2, 3 to 11. And now, I make the line. Okay? Now, how about this? How about this? If you know, if 1 knows 2, there's a line between 1 and 2. If 2 knows 3, there's a line between 2 and 3. If 3 and 4 do not know each other, there's no line between them. So, I can record relationship. Notice, it's very good at relationship. Okay? So, ultimately, the world, if you can conceptualize data into picture, you're good. Number 1, table. Number 2, graph. Let me show you how it works. Well, I can, in the future I'm going to use that as a whiteboard, but today I'm just going to, well, let's Excel. Okay, I'm just going to make something up. This is what the table looks like, right? Say name, okay, Bob, Alice, A for Alice, B for Bob, C for Chris, D for David, okay, E for Alice, E for Elizabeth, okay? Actually, we don't need that many. Okay. Now, what makes this a tabular data? Well, because I have height and I have weight, right? So if I fill, you can fill all this, right? Why is this a table? Yes, it's a table. Look, row, column. Most of the time it goes like this because think of an Excel, right? There's a lot more rows than there are columns. So chances are the attribute, so the attribute go this way, okay, age. But the data, the number, you can have millions of people, so go down this way. Okay, does that make sense? Okay, so that's a table. Now, what if I want something else? I want something like, does Alice know Bob? I can do this. Alice, Bob, and Chris. Okay. Alice obviously know Alice, so I can put one there, but that means nothing. Okay. Okay. Let's say Alice and Bob are friends, and Chris doesn't know anybody. That's it. So, Alice is a friend of Bob. Bob is a friend of Alice. Right? Does that make sense? So this is still in tabular form, but think of it, this is kind of like clumsy. So imagine that a database literally store Alice, Bob, and Chris, and Alice store connection to Bob. So you would have Alice, Bob, Chris, and Bob and Alice has a line between them. Okay. Now, this ultimately is a square matrix. So they call it adjacency matrix. Okay. Adjacency matrix is a way of recording graph data into tabular form. You can think of it this way in the first instance. But if you think about it, what if, imagine the world worked out differently. Nobody invented spreadsheet. Nobody's invented table, a database. But Neo4j came first. Okay? In which case, you would have database that store Alice, Bob, and Chris, and each one has a connection or no connection. So Bob and Alice has connection to each other, right? Now, I say, wait a minute, I want to store some information about Bob and Chris. How would I do that, guys? Remember, we don't have tabular database. We don't have Excel. This is a universe without spreadsheet. What you would do is you would consider this a vector. Call it an attribute vector and stick inside the circle called Alice. So, in this example, I have tabular data. I add matrix, adjacency matrix to denote relationship. But if I started off with a relationship database that had Alice, Bob as circle and line as connection, right? And I want to add height, weight, and age of individual person, how would I do that? I would stick inside this a vector. Stick inside this a vector. Stick inside this a vector, and these are called attribute, node attribute. Okay. Don't worry if this looks a little bit weird, because you didn't grow up in the world of graph database. You grew up in the world of tabular database. Fine. That's not a problem. And in fact, as I said, to get a job, to work, blah, 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 nobody's going to mind if you don't know graph database. But if you don't know tabular database, they probably won't hire you. Okay? In fact, you can finish an entire career in a bank. In fact, most people finish their entire career not knowing a thing about graph database. Because this kind of relationship data only gained prominence in the last 20 years. Okay? So the word graph data structure was kind of a weird kind of, why? Why would you care about relationships so much? Right? But now in the world of Facebook, you're almost defined by your network. The world has kind of like gone the other way around. In a network or in a social network, who you are, your height, your weight, your age, almost doesn't matter. What matters is how many people likes you, or how many people links to you, or how many follow you. So it's almost like the note, whatever is in there means nothing. It's the connection that means everything, right? Now, imagine the world in which Facebook came first and nothing else mattered. Maybe the first database developed would have been graph database. The point is this. If you appreciate these two constructs, tabular data, graph data, then all other exotic data structure, leave it to data scientists or leave it to computer scientists. Okay, people who are doing the back-end heavy-duty database engineering. Those guys have to know, because database, they're not just conceptual, they're computational. So it depends on certain database design, there's a speed, right? There's a speed. For example, if you care about relationship, if you store things as a graph database, who does one know? One knows two. It's very quick, right? But if I use a tabular database, who does one know? Well, one is Alice. Alice has one corresponding to Bob. Oh, Alice knows Bob. Okay, you can imagine that there's an efficiency gain or loss by designing the right database. And that's why professional database engineer, they have to learn about really exotic database, data structure, linked lists, and hash, and this and that, and dynamic database, static database, mapping. Oh, I have no idea. These people, way more technical than I am on that. Okay, but you don't have to, because conceptually and in some way, practically, you only need to know to appreciate two paradigms: table, graph. Okay, and by now you should know that graph doesn't mean plot. Okay, so from now on, never use the word graph for what you saw in high school as graph. Whatever you saw in high school as graph, you should call it plot. Okay, a graph literally means nodes with connection. Okay? Another word you're allowed to use the word for is network. But, so you can see, so this is basically, tabular data native to tabular. This is graph data, but sort of like stored in table form. Okay, so we don't need to do that. Right, now, in the textbook, again, hopefully it should be ready by Monday, okay? Just basically, you can buy it from the lady or whatever. Okay, you will see when you open, just by page count alone. In fact, graph data is treated as a separate chapter, the last chapter, chapter 7, right? Whereas supervised learning, unsupervised learning, probabilistic model, this is all mostly going to deal with tabular data, okay? And that's real life as well. And this is data analytics versus machine learning. I do spend a lot of time on this, and in fact, we'll talk a little bit about that. And the concept of artificial intelligence, computational intelligence, digital intelligence, this is worth knowing. It's worth knowing. Right? Again, starting from AI inspiration, intelligence in that sense just means human-like, right? Then you have a second meaning of intelligence, which some of you may not appreciate, and that's military intelligence. There are two words that uses that: military intelligence and business intelligence. They mean the same thing, just different contexts. That intelligence means it's some kind of information that's not public, very expensive to obtain, But once you got it, it gives you some kind of competitive edge, right? So obviously, military intelligence is very expensive, right? Because to find out, you have to send some guy with a binocular and a lot of camouflage and crawl deep into enemy territory and say, you know, how many tanks they've got and so forth, right? Those are very valuable information. Gives you competitive edge in war, right? Is it expensive? Yes. Because if that guy is caught, he's dead, right? He's shot, you know? Spy. Well, same with business intelligence, but a lot less bloody, right? Illegal thing is industrial espionage, okay? But we're not talking about illegal stuff. We're talking about legal business intelligence, like I would like to know how much or how well the competitors' interaction with consumer is. Okay, is the consumer loyal to their brand? Are they stepping up? Are they coming up with a new thing? So these are not necessarily something that you would have to break in and get a secret, right? But you can sort of like, hey, wait a minute. Honda is looking at Yamaha. Yamaha just filed a patent for this kind of suspension. Public information, right? Not illegal. Hey, is Yamaha thinking about new kind of motorcycle? Right? These are not something that's readily apparent. And with military intelligence, obviously, you focus on the enemy. With business intelligence, you focus on the competitor, right? But with business, I don't want to use the word competitor. I want to use the word counterpart as a more general. Because you don't just want to know information about your competitor. You also want to know information about, how about your employee, right? Are my employees happy? I don't know if you have parents who work in a corporate environment, lately they'll be doing things like 360-degree evaluation or engagement survey. That's exactly it. In that case, the company is thinking with an employee and trying to get intelligence or information about their workforce. If the workforce is happy and engaged, great. If not, first of all, they can just leave. They're more likely to leave for a minimum upgrade in salary. Also, if they're not engaged, they would just give minimum effort. They would not be creative, right? They would use their creativity for weekend hobbies, photography or something like that. But if they're engaged, you know, this company has a mission, want to clean up the world and make money in a sustainable way and be a force of good for the society, then chances are its employee is going to be very creative, coming up with solution, business, innovation that would help propel the company's mission. As opposed to, well, I'll just clock in from 9 to 5, and then I will reserve my creativity for photography or something like that, right? So business intelligence is a big deal in terms of HR, human resource as well. Right. Computational intelligence, that's basically my concentration for my doctoral degree, okay? A bit of a background, I did, I may have said this before, but Basai is more like a art and science integrated, right? Well, this is kind of, in a way, inspired by what's called liberal arts education, which is what I'm used to. So when I was in the United States, as an undergraduate, I enter a university. Okay. It's not like here. Here, you enter into Basai program. My daughter enters into communication arts. My son enters into to medical science. Okay, so you go to a different school, different department. Well, with liberal arts, you go to a university, right? You don't go to chemistry, physics, mathematics, literature, or history. You go to university. If you're a graduate student, yes, you go to different department. If you're a faculty, yes, you go to different, you're a lecturer in chemistry, in physics. But my background is a liberal arts, so it's a bit like Basai. So I could take any class, basically. and I take concentration. My concentration was in physics and economics, double major. So basically, I took a lot of class in physics, took a lot of class in economics, and well, there is actually a nice story. When I was an undergraduate, this was in a winter. To save, I guess, money, undergraduate dorms are closed over the winter because most people go home anyway, right, in the United States. And the undergraduate have to move into graduate dorm. So I moved into graduate dorm. And there was one guy come from Argentina, I think, to study master in operations research. So I got interested in operation research. And eventually that became my master as well. So I studied master in operations research. And operations research, never mind, long story short, it's applied math to solving real world problem, optimization, modeling, and optimal control and all that stuff. But during the operations research study, I noticed that a lot of class begins with assumption, assuming the search space is convex, right? Assuming this, assume linearity, assume this, assume that. So I thought, what if the world doesn't assume? What if the assumption fail? You don't do anything then, right? So I study sort of something that has less assumption. Doesn't have to be convex, doesn't have to be smooth, differentiable, doesn't have all these niceties. If it doesn't have all this nicety, to solve it, sometimes you have to use computer. And so when I, got a scholarship to do a Ph.D., and I started my Ph.D. at Imperial College, basically I focused myself to what's called computational intelligence. So computational intelligence, like, it's not just intelligent in the AI sense that it's human-like, but intelligent in the sense of clever solution, optimal solution, best solution, most profitable, least waste. Okay, so it's kind of intelligent in that sense, but it doesn't rely so much on mathematical assumption as my master, which was in operations research, that one, So this computational intelligence, this is the sense of solving intelligent solutions, solving for intelligent strategy, solving for intelligent control, solving for intelligent policy, solving for intelligent solution, optimal solution, based not necessarily on, say, differential equation or mathematics. Yeah, there will be mathematics. You can't escape from that. But the algorithm used to solve it sometimes is framed as a computer algorithm. In other words, a recipe that tells computer how to compute the next step from this step, and then next step from this step, and then next step from this step, and then next step on this step, until you stop at the best solution you can get. So that becomes the basis of computational intelligence. Now, but strictly speaking, computational intelligence, so intelligence in that sense is intelligent solution. There are three things that fall under computational intelligence. One is a big umbrella called neural network research, artificial neural network. This is what eventually becomes what you guys know today as AI. Okay, although the term AI came before that, but this strand of research, neural network, became the core of it. ChatGPT, convolutional neural network, all this thing came from artificial neural network, which is like a big chunk of computational intelligence. The second chunk of computational intelligence has to do with mimic the way nature optimizes. You know about evolution, right? Charles Darwin, right? How does species happen? Species is a solution to one problem, survival. Survival in acidic soil with no humidity, that's a challenge, that's a problem. Solution, some kind of grass in the desert. The problem was survival in a thick jungle that has leopard on the ground, but fruits on the tree. What's the solution? Monkeys, right? So evolution is kind of evolving solution to a survival problem specific to the environment. Now, some clever people in computer science thought, wait a minute, what if we simulate animals? Animals that can breed, produce children, except instead of surviving based on climbing trees and surviving based on arid land, the survival is a mathematical function that optimizes profit. What if instead of optimizing survival, you minimize travel time for logistics in a truck company? So now you evolve truck logistics using simulated population of quote-unquote computer animals. So that becomes evolutionary optimization. By the way, that I started with AI, neural network research, but I ended up doing maybe 80, 89, 90% of my PhD thesis in evolutionary optimization. Keep that. Finally, another part of computational intelligence is, well, you can have computer that's intelligent, but does it solve human problem? Computers are good at solving numerical problem, but what if human beings have criteria like hot, cold, risky, financial return, sustainable future? Is there a map that maps human criterion into mathematical numbers? Something like that. And so this goes under the whole rubric of human-machine interface or interaction. Okay. In hardware form, you've heard of Neuralink, right? That's also an interface. So man-machine interaction, man-machine interface, cybernetics, sometimes you've heard of that word, became the word for cyborg because if you have cybernetic implant, they call you cyborg. Anyway, so cybernetics, human man-machine symbiosis, that's also human computational intelligence. Because to get an intelligent solution, you have to combine something that's computable in a machine with something that basically works with human being. Finally, the word digital intelligence. Basically, the word digital intelligence now, you can use that instead of computational intelligence. You still do these three things, but you can do anything and you can talk about a lot more. The point is that all of these have one thing in common. Whether or not coming up with smart solutions, simulating nature and evolution, or coming up with mathematics that solve a problem in a way that has a good symbiosis or interface with human being, or IoT data, or distributed drone, all kind of thing, all kind of intelligence that's coming. The only thing that has, the one feature that is in common with all this is that it's based on digital information. Everything is processed through digitized data. So now, you would not use the word computational intelligence per se. You probably use the word like digital intelligence, which is why Basai has applied digital intelligence track, right? But anyway, so to me, digital intelligence is a bit of a new term, but I think it's okay. I'm happy with that, okay? But if anyone asks, my PhD is in computational intelligence and operational research, also a bit of my master. Okay, so this is how intelligence is defined. Okay. And this is kind of a nice little relationship. By the way, this is a graph, but this is not a data. This is actually a diagram. Literally, I want to say that, data can be visual, quantitative models, statistic, machine learning, but this is an interactive visualization. Never mind. Right. How much time we do? Okay, good. Now, we are heading toward a big chunk of this is based on machine learning. Now, I already gave you a little bit of lay of the land description. Why does machine learning work? Well, machine learning was originally used because you want to create an AI, but you can't program if then, if then, if then. If the question is how are you, answer is fine, thank you. You can't do this, okay? So you have to get the computer to learn from data. So the way you program is you program a computer that has an input as a batch of training data and use that to sort of like do some algorithm, and that algorithm is called training. Okay, so they call it training, which is an analogy from how human beings learn. Human beings learn sometimes from training. Okay. Now, these are different details that I give you to you read and more like that. But what I would like to do is finish today by pointing out the main what's called paradigm of learning. Okay. Not you, I. Yeah. When I was your age or later when I was doing neural network research, it was about training multi-layer perceptron artificial neural network of some architecture. Eventually, they start to crystallize the concept of machine learning along 3 paradigms. Okay? And that 3 paradigms mimics. Again, you can't program computer if then, if then. You have to program computer to learn. What else learn? Human beings. How do human beings learn? There are actually 3 paradigms that human being learns. I bet you didn't know that, right? Well, think of yourself. When you were just a baby, you were equipped not with knowledge, but with sense organ. You can smell, you can feel, right? You have a positive, negative scoring system that something is pleasant, something is yucky, right? So that's what you were equipped with. What happened first? When you open your eyes, you start to see things, you smell things, you associate the smell of your mom with warm milk, right? And being full. Later on, maybe you associate the sight of your little sister with your bigger sister with your bigger brother, okay? All of this, you begin to associate the sense. So it's sort of like smells of mom comes with nice and feeling, okay? Sound of a dog comes with something scary, okay? So you start to do this kind of auto-association. Who taught you this? No one. Your parents can best provide the environment, right? Hopefully, your parents don't drop you in the middle of a zoo with you know, lions and whatever, right? So your environment is kind of nice, but sometimes your dog comes in and smell and it's like, you don't like that. That's too rough, something like that, okay? So maybe your older brother and yell at each other. Okay, you can't control that. The point is you make all this without your parents knowing. So you're learning completely unsupervised. This ability to categorize, put things together, associate this with that, that with this with that. This is probably that, this is called unsupervised learning. And that is one chapter, because that is a way of building machine learning. So there's one, so we mimic that. So there are unsupervised machine learning algorithms. Okay? Now, later, your parents start to teach you language. And that language has to have some sort of input, output, prompt response kind of thing. What's this, little Johnny? Right? This is an apple. So your parents giving you this with apple, this with orange. Not only that, not only is parent giving you the pairing of this picture with orange, this picture with apple, you have to try. What's this, Johnny? If you say orange, good. If you say apple, no, 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 no. So the parents give direct feedback, right? So there's an input-output pairing, picture and identification. This is your brother, Alice, John, whatever, I don't care. Right? If you give the right identification, good. If you give the wrong identification, no, 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 no. Say it again, right? So there's an input-output example for you to learn from. And you have to do your own input-output, and then you will be graded immediately, whether or not you're correct or wrong, right or wrong. Okay? Right? That's like immediate exam. It's not a term exam. Now, that's called supervised learning, because your mom has to be there to say this is right, this is wrong, give immediate feedback, encouragement. There's also supervised machine learning algorithm. There's a whole class of them. Finally, third, okay, you may have seen already there's 4, but I'm going to say 3. This is called reinforcement learning. What it means is this. Unsupervised learning, you just do your thing. You grade yourself, you say, you associate this. And if it's not right, you adjust it. Nobody's going to give you feedback whether or not you're right or wrong. Supervised learning, you're given immediate grading. Then you go to kindergarten. If you behave in a certain way, you share your toys, you come to class on time, people like you. You come to class late, you scream out of turn, you don't share your toys, you fetch some other kids' toys. After a while, kids don't like you, right? This is kind of a longer evaluation loop. It's a behavioral scoring. It's not what you say, it's the behavior over time in different situations. When it comes to lunchtime, do you steal other kids' food? When it comes to playtime, do you steal other kids' toys, right? And over time, the good behavior gets reinforced. People like you, okay? If you're disrespectful to your teacher, show up late, steal your friend's toy, nobody likes you, right? That is called reinforcement learning. And those are the 3 human learning modalities that we apply to machine. Okay? Now, in this class, we will not touch reinforcement learning. The reason is reinforcement learning is mostly or more applicable to what's called optimal control problem, like controlling a robot, controlling autonomous drone. Think about it. If you have something that scores over behaviorally over time, what's the analog of people not like you? Well, robot running into stuff and breaking things, right? What's analog of people liking you because you're doing the right thing? Well, robot that doesn't bump into things and park the car really nicely. So reinforcement learning is a lot more relevant to things like this kind of trajectory, okay? Robotics. Not all problem is robotic. For example, I keep saying, and most people don't realize this, but central banking is an optimal control or reinforcement learning problem, because you have to learn how to manipulate the interest rate so that the economy doesn't bump into things. What do I mean by bump into things? Too much inflation, that's bumping to the right. Deflation, that's bumping to the left. The Bank of Thailand has this corridor, just like you have a robot that has to go into a corridor, doesn't hit the right, doesn't hit the left. Bank of Thailand has a corridor. It's called inflation targeting. If the inflation is too high, no good, people suffer. If the inflation is too low, no good, people suffer. Let's control the trajectory of the economy so it's sort of like live between this upper and lower corridor. It's very difficult. But that's optimal control problem. Same thing as, so anytime you have this kind of trajectory, bumping into things and, preserving the integrity. So so for this class, we will have, and therefore I only wrote chapter on unsupervised and supervised learning. Finally, okay, there is this thing called representation learning. This one is not motivated by human being. And this one only became a predominant paradigm in the last 5 years. It's about learning how you can represent things numerically. Okay? Now, I told you that we're talking about data analytics and essentially we deal with numbers, right? So in this class, there's no language model, for example. Okay? We'll do a little bit with word example, with frequency and stuff, okay? But we won't be doing GPT or anything here, okay? What? Those, before anything can happen in ChatGPT, the first thing that happens is you have to map words into vectors. It's called word embedding. And the 300 I mentioned earlier is what we do with word embedding. It's about 300 long vector, okay? It's called representation learning because once people realize, hey, machine learning is so powerful, AI is powerful, but you have to turn your object of analysis into numerical form, into vector, right? And you turn word into vector. What else can you turn into vector? How about molecule into vectors? How about genomic data into vectors? How about relationship into vector? So you have this generalized turning things into vector. The thing is that turning things into vector is only necessary because you're dealing with a computer, right? Right? I don't need to turn word into vector before I speak, right? Because I can process word directly, okay? So this thing also requires learning. So it's a machine learning paradigm specifically, not as an end in itself. They call it so that you can embed object, words, picture, relationship, molecular construct, gene data, games, graphics, all this, memes, into vector. And once you turn into vector, you can do all kind of stuff down the line. And this is where classification, identification, this, supervised learning, unsupervised learning kicks off from here. So it's sort of like a pre-staging. There's like a representation learning, put it down here, and then supervised learning, unsupervised learning take over from here. Okay? So that thing doesn't have a human analog because you process word directly, right? You don't turn word into number first before you start speaking. Okay, so that one also is not in this class. So there are 3 paradigms basically conceivably motivated by human learning. 2 of which are relevant to data analytics. One is more like either central banking or robotic control, some kind of trajectory. And then you have representation learning. So we'll focus on this. And this would be chapter 4 or 5, I think. Okay, I hope you understand the game plan. Okay, now when you get the book, okay, we'll get through that. So it's kind of, I think you probably have it easy compared to the previous class because at least you can look ahead in the textbook and come back and so forth, okay? Which means I'm going to be a bit more demanding of your proof of learning, right? Your exam's going to be tougher, hopefully, right? I'm going to give you, you can take the physical book in there, in the class, but in the exam, but then, okay. Whereas previous class didn't have that, so I just gave them something very simple and silly to do in exam. Okay, so hopefully your project as well will reflect this. Will be more complicated. We will be more nuanced. Okay, but I still think that solo project is the way to go. We'll see. We can talk about that. Okay, we'll have and then throughout we'll have 1 or 2 workshop, which means that you can spend the time talking among yourself, but one of the thing I like to do is just, well, come talk us through. What are you doing? Okay, and this is a very good exercise, whether or not it's in a corporate environment, in a fintech, in a startup environment, or even when I was in a graduate school. The idea of this is what I'm working on, guys. Okay, this is what I'm working on. Can you help me? What do you think? I'm having a problem here, or can you make suggestions? You can make positive feedback. You can be curious. You can ask. And when you have a bunch of bright people talking to each other, and one guy just put his thing on the board out there, let me put out there, guys, this is what I'm doing. What do you think? That's a very good thing. Okay? And then you would have to try to help your friend. You know, this is what it means to be, I guess, positively critical, right? Okay? So let's try that. Let's try that. Yeah. So I think that's let's just about wrap up this today's lecture. Yeah, next class you will have Mathematica install, and then you will go, you know, line by line almost. It's again, it's for those of you who knows a little bit about computer, there are different what's called programming paradigm. We talk about machine learning paradigms, right? Now we talk about programming paradigm. There's object-oriented. By the way, this was my favorite. My PhD was based on object-oriented paradigm. There's procedural, there's declarative, there's functional. Well, Mathematica, in this sense, a bit like Python, in that you can, with Python, you can use Python to program in an object-oriented style, but it's not natural. The most natural thing to do with Python is functional programming. Same here, same here. The most natural thing to do is functional programming. Having said that, this is also more of a declarative in the sense of, I would like to have this done. Okay, so it's more top level. That's why it's more appropriate for say sustainability or health and well-being student who wants to do a top level. Please build me a classifier machine. Now, top level is like has a whole bunch of default. This is how you do it. With declarative / functional, what you do is you hide a lot of detail, and you make a lot of commonsensical default setting. So I would like to build a standard classifier, object classifier. That's declarative, right? So you don't give it a lot of detail. Everything is by default. Default uses kind of stuff. But if you know what you're doing and you want to fine-tune and optimize, you can specify the class of function, the procedural aspect, so you can dig deep. So you start from, I don't know, I have this data. I would like to sort of like see if they fall into cluster. That's declarative programming. But more functional programming, hey, I want to use a density base. And once you got density base, I want to display the plot of all my data in a reduced dimension so I can see that they are separated. You know, more functional, more detailed specification. But you don't need to go all the way to procedural. Okay, that's two-way down. That's like for I equal to 1 I plus loop I time or something like that. Rarely do you do that. Sometimes you do, in Python, you do that with list comprehension. That's a way of sort of like embedding procedural programming in functional programming. Okay? Anyway, but it's very powerful. We'll talk about it next time, but it makes no sense until you have that in front of you. Okay, it makes sense. And okay, so we're doing good on time. All the arrangement, I think everybody's online, right? Okay, and I don't really respond or read much, but you know, definitely Dimutu is again, he's very popular with students. He's very he cares about you guys. So if you have any problem, chat with him. Okay, and try to get your thing sorted out by Monday, and I'll try to get the printer hopefully by next Tuesday, but definitely by 2 weeks. Okay, okay,ครับ. If unless you have got anything, so that'll be the day. Nope, that is the day. That's today. Okay, I'll see you next week. สวัสดีครับ